Hi, my name is Udit and I'm a fifth-year PhD student at Harvard University. Today I will be presenting our work in collaboration between Harvard and Facebook AI research on understanding the environmental footprint of computing. Now, while the environmental footprint of computing is a multifaceted problem, today we're going to be focusing on one particular dimension of this challenge, namely carbon footprint. Over the last 20 years, we've seen hardware and software advances dramatically improving performance and energy efficiency. But the question that we're interested in today is, how have these advances affected computing's overall environmental sustainability and more specifically, its carbon footprint? Now, recent studies have shown that when we combine emissions from operating mobile devices, communication systems, and data centers, computing's overall footprint continues to grow. In fact, in 2015 alone, information and computing technology consumed over 700 million metric tons of CO2, which is equivalent to roughly half the entire aviation industry's overall footprint. Estimates also show that if this is left unchecked, the emission factors will continue to grow and even double over the next decade. Now, while the exact rate of increase is challenging to predict, there are many reasons why we should expect the overall footprint of computing to grow over time. First, only 59% of the world's population is currently online. As more people gain access to reliable internet connectivity, we should expect more mobile devices and data centers, causing an increase in the overall carbon footprint of computing. Next, with emerging applications like AI, AR/VR, autonomous driving, and scientific computing applications, the demand for computing resources will continue to grow. And finally, in addition to the higher compute demands, improving efficiency will become increasingly harder. Already, hyperscale data centers are operating at a near optimal PUE of around 1.1. And as Moore's law slows down, realizing large efficiency improvements across the entire computing landscape, from mobile devices to communication to data centers, will become even more challenging. Now, given these challenges, there has been an increased focus on sustainable computing over the last few years. For example, environmental sustainability has been of great interest to many researchers. Last year, Bobby Monet gave a keynote at Micro on the challenges and opportunities of architecting a sustainable planet. The Zero Carbon Cloud Project at University of Chicago designs sustainable, renewable energy-driven cloud computing resources by exploiting stranded power. From the applications and algorithm side, the AI community has been characterizing the large carbon footprint of training state-of-the-art natural language processing models. And from the circuit side, researchers have been developing device-level environmental cost models. Now, in addition to researchers and given the growing environmental impacts of computing, technology companies are also really interested in looking towards sustainable computing. For instance, companies like Google, Microsoft, Facebook, Apple, and Amazon have all pledged to reach carbon neutrality over the next decade. In this talk, we explore what role computer systems and architecture researchers and developers can play in achieving sustainable computing going forward. Specifically, we ask the question, where does computing's carbon footprint really come from? Now, in our journey to answer this question, what we found was quite surprising to some of our collaborators that have spent a lot of time thinking about hardware performance and energy efficiency optimizations. In particular, what we found is that computing's carbon footprint not only comes from energy consumed by running applications on mobile and data center hardware, but also from manufacturing those hardware platforms themselves. Now, to better understand the source of computing's carbon footprint, in this talk, we'll break down the carbon footprint in three ways, focusing on mobile, data centers, and semiconductor fabs. Now, the key insight of this work comes from analyzing dozens of publicly available and validated sustainability reports for different technology companies and hardware platforms in order to understand the underlying trends in computing's overall carbon footprint. What we find in particular is that in many cases, the carbon footprint from manufacturing hardware, also called embodied carbon, can dominate that from energy consumption itself. And finally, Given our understanding of carbon emissions, we're going to conclude this talk by charting paths for how to design the future sustainable computing systems. First, we'll break down emissions in mobile systems. Now, to study the breakdown of carbon emissions in mobile devices, we use a tool called Lifecycle Analyses, or LCAs. LCAs are frequently used to quantify the emissions across 4 phases of products. Now, these products can also include hardware systems. The first phase is manufacturing the product or hardware platform. The second is transporting it from fabs to users. The third is using the actual hardware device. And the final phase is recycling and end of hardware lifecycle processing. Now, since portions of the hardware platforms can be repurposed for future iterations, we have a back arrow from recycling all the way back to manufacturing in order to form and close a loop on this hardware lifecycle. Now, when considering the carbon footprint of computing systems, software, and hardware designers typically focus on product use or energy consumption. However, through our analysis, what we find is that for many use cases, hardware manufacturing can also contribute a significant portion of emissions to the overall hardware lifecycle. Now, where emissions from hardware use can be thought of as coming from OpEx-related activities, we can think about emissions from manufacturing as coming from CapEx-related activities. Now, here we look at the breakdown of Apple's overall company-level carbon footprint of around 25 million metric tons of CO2 in 2019. The hardware lifecycle-related emissions are broken down into manufacturing, shown in red, product use or energy consumption, shown in green, transport in blue, and recycling in black. What we find is that, in fact, life cycle emissions account for nearly 98% of Apple's end-to-end carbon footprint. The remaining 2% are shown in the gray category over here and come from activities like business travel and other company-level activities at Apple scale. Now, as shown in red, manufacturing accounts for about 74% of Apple's end-to-end breakdown in 2019. Hardware use accounts for about 19% of emissions. Now, here the majority of the product use related emissions are devoted to iOS devices like phones and tablets, followed by devices that are using macOS like our laptops. Now, this is including the emissions over the course of the lifetime of devices, which is around 3 years for mobile phones. Now, within manufacturing related emissions, we find that integrated circuits account for nearly 33% of all emissions. This is more than the emissions due to boards and flexes, aluminum casings, displays, and other electronic components. Now, the integrated circuit emissions are largely due to designing and manufacturing SoCs, DRAM, and NAND flash components in mobile devices. Now, these are directly related to the hardware design and development practices in computer architecture. Now here, what we've been looking at is the emissions aggregated across hundreds of millions of phones and iPads and consumer devices that are sold each year. Next, what we want to do is study the emission breakdowns for individual hardware platforms. So here we're looking at the carbon footprint breakdown of individual mobile devices. On the x-axis, we have 8 mobile devices, the first 4 being battery-operated ones like iPads, iPhones, Apple Watches, and laptops. The last 4 are always connected or plugged-in devices like personal assistants, desktops, and gaming stations. On the y-axis, we have the absolute carbon footprint in log scale. In black, we see the end-to-end lifecycle emissions, in red, the manufacturing portion, and in green, the emissions from hardware use and energy consumption. Across the battery-operated devices, we find that roughly 75% or 3/4 of emissions for the end-to-end hardware lifecycle are actually coming from hardware manufacturing itself. On the other hand, for plugged-in or always connected devices, we find that the majority of emissions are coming from energy consumption. And about 1/3 of the footprint is coming from hardware manufacturing. Now, we attribute the differences between the carbon footprint breakdown between battery-operated and always connected devices to come from varying user behaviors. For example, they have different frequencies of use, different types of workloads are running on them, different idle and sleep cycles. and the lifetime of the hardware that's being used. Now, another interesting point that we see from this analysis is that the overall and manufacturing related carbon footprints are not one-time static costs. Instead, they seem to scale with the hardware resources available within each hardware platform. Now, in the paper, you can find additional details about the carbon footprint breakdown across an even wider range of mobile devices. But for now, what I want to do is look at another cross-section of this design space. Namely, how does the carbon footprint of devices scale over time? So here we're looking at the trade-off between performance and manufacturing-related emissions. So on the x-axis, we have mobile net V1 inference throughput gathered from Geekbench measurements. And on the y-axis, we have manufacturing-related emissions gathered from publicly available sustainability reports from lifecycle analyses of devices with similar storage capacities. In yellow and green, we have example mobile devices from 2015 and 2016, respectively. And through the letters H, we're denoting devices that are coming from Huawei. With A, we're denoting devices from Apple. And with G is going to be Google. Now, adding the devices that were available in the market in 2017, we find that the Pareto curve is starting to form between mobile performance and manufacturing-related carbon emissions. Now, further analyzing devices from 2018 and 2019 in black and red, respectively, we find that the Pareto frontier from 2017 to 2019 has strictly shifted towards the right. Now, as a result, while performance has improved, carbon footprint has not. These performance advantages are a direct result of all of the algorithmic and hardware improvements that the hardware and software community have been investing in. Now, moving forward, what we really need to do is think about ways to not only shift this Pareto frontier to the right, but also downwards in order to lower emissions. This includes thinking about things like carbon-aware resource provisioning and increasing the lifetime of hardware used. In fact, in the paper, we show that it takes over 3 years of continuously running AI inferences on a Pixel 3 phone for the carbon footprint from energy consumption to equal that coming from hardware manufacturing. Now, 3 years is the average lifetime of our mobile phones. This highlights the need to think about extending hardware lifetimes through increased reliability and future-proofing hardware to provide sufficient performance on emerging applications. And more generally, we need to think about lowering the footprint of mobile devices as it's a crucial step towards enabling a future of sustainable computing. Now, given the mobile footprint, we next look at the breakdown of carbon emissions in hyperscale data centers. Now, in addition to implementing server-class hardware, these data centers are beginning to be powered by renewable energy, which greatly impacts their overall emission breakdowns. Now, to study the breakdown of emissions at the data center scale, we use something called the Greenhouse Gas Protocol. The GHG protocol is used by many companies, including technology companies like Google, Facebook, Amazon, Apple, and others. And it categorizes emissions with 3 key scopes. First, scope 1 quantifies the emissions directly from burning diesel, gas, and refrigerant from facilities and data centers. Now, next, scope 2 quantifies the emissions from purchased energy. This includes the impact of buying renewable energy in order to offset the net or average carbon footprint from energy consumed by the data centers. Now, this net emission factor does not ensure that every unit of energy consumed by the data centers comes from renewable energy itself, but rather the average carbon intensity of the energy consumed. Finally, we have scope 3, which comprises emissions from the supply chain. Now, depending on the company, the supply chain can be separated into the upstream and the downstream components. The upstream components typically include things like capital and purchased goods. So in the context of data centers, this really comes from hardware servers and the manufacturing overheads of them, racks, data center infrastructure, and construction. On the other hand, the downstream supply chain and scope 3 emissions comprise of the use of sold goods or hardware systems. Now, note that in the context of data center-oriented companies, which is what we're going to be looking at, like Facebook and Google, scope 3 emissions are typically dominated by the upstream component. And taking a step back, in terms of these data centers, scope 2 emissions, we think about them as coming from OpEx related activities. On the other hand, scope 1 and 3 emissions are coming from CapEx related activities. So here we're looking at the historical trends in Facebook's carbon footprint using this GHG protocol. In blue, we see the net scope 1 emissions, in green, the net scope 2 emissions, and in red, the net scope 3 emissions. On the x-axis, we're looking at the breakdown between 2014 and 2019. On the far right, we see the impact of Facebook purchasing renewable energy as the difference between the black dashed line and the green line. We see that scope 2 emissions greatly reduce when we power these data centers with renewable energy. Now, following the mobile analysis, we find that scope 3 dominates Facebook's carbon emissions. In fact, nearly 49%, or about half of these scope 3 emissions, are coming from hardware manufacturing of the servers, infrastructure, and data center construction. Now, interestingly, if we're looking at this plot, we also see a large increase in Facebook's scope 3 emissions between 2018 and 2019. This increase is primarily due to a change in the hardware footprint disclosure practices. Now, in particular, prior to 2018, the carbon footprint related emissions from manufacturing servers found that the data center were not included in the publicly available sustainability reports. After 2018, hardware manufacturing emissions began to be included, causing this large rise in scope 3 emissions. Now, the change in disclosure practices highlights the need to motivate companies to report their carbon emissions over time. In fact, we're seeing similar trends across other data center-oriented companies as well, like Google. And you can find some of these details in the paper itself. Now, so far, what we've seen is the importance of looking at both carbon footprint from energy consumption and hardware manufacturing across mobile and data center devices. Now, next, we look at the source of these hardware manufacturing-related emissions, in particular, the semiconductor fabs. In particular, we study whether the use of renewable energy at fabs can reduce or eliminate the manufacturing-related emissions in hardware life cycles. To study the role of renewable energy, or what role renewable energy may play in hardware manufacturing, we look at the breakdown of emissions in semiconductor fabs. So here we're looking at the breakdown of emissions for wafers manufactured by TSMC based on their publicly available sustainability report. On the x-axis, we see the impact of using renewable energy to power fabs. The range spans a baseline coal-powered fab all the way to a renewable energy power fab using solar or wind energy. Now, this range encompasses a reduction of carbon intensity of around 64x. And on the y-axis, we're seeing a breakdown of these emissions. In green are the emissions from powering the fabs themselves, which are reduced when fabs use renewable energy. We find that even with optimistic improvements of 64x in carbon intensity, the fabs reduce their overall footprint for each wafer by around 2.5x. The remaining footprint comes from a combination of burning chemicals, gases, PFCs, and raw wafer materials. Now, in comparison, TSMC has aggressive plans to power its fabs with 25% renewable energy by 2025, as you see by the orange marker over here, and 100% by 2050, as shown by the blue marker over here. Now, despite these aggressive plans to reduce the operational related emissions from fabs, the carbon footprint of hardware manufacturing will persist into the future. Thus, we really need to start thinking about these remaining emissions and their impact on the hardware design process in order to realize sustainable computing going forward. So far, we've seen the importance of considering end-to-end hardware life cycles in order to understand the carbon footprint of computing. Now, based on this analysis that we've seen, I'd like to wrap up this talk by exploring some ideas for enabling sustainable computing going forward. Now, typically, when we think about optimizations for sustainability, we consider ways to improve performance and efficiency. However, performance improvement is not enough. Following Jevons paradox, higher efficiency can actually lead to higher application demands, which overshadow the benefits from improved efficiency. One example of Jevons paradox at work is AI. So here we see on the x-axis As AI hardware software performance has improved or doubled on the x-axis, model sizes have actually also continued to grow. For example, given the hardware software improvements, we've seen that the size of state-of-the-art NLP models has grown by 3 orders of magnitude in the past 2 years. Similarly, Facebook's recommendation models, which consume the majority of their AI training and inference capacity, have grown by an order of magnitude in just the last 3 years. Now, given Jevons paradox, sustainable computing requires designers to consider the carbon footprint as a first order metric. Reducing carbon emissions is going to require cross-stack optimizations, targeting emissions across the entire hardware lifecycle, including both manufacturing and operational use. This will take collective efforts from technology companies across the computing stack in terms of increased reporting and optimizations. Now, furthermore, we need to investigate methods to enable scaling computing resources for emerging applications and growing number of users, while balancing the environmental effects of these growing demands. In addition to industry, we need research across the computing stack in order to realize sustainable computing. At the application and algorithms level, we need to design methods to efficiently use hardware platforms. Next, we need carbon-aware resource provisioning and techniques to enable higher heterogeneity to reduce hardware footprints for applications. And at the architecture and circuits level, we need to revisit the role of dark silicon and design techniques for low footprint logic and memory systems. Now, to recap, in this talk, we explored the environmental footprint of computing. In particular, we saw the importance of optimizing end-to-end lifecycle emissions, including both CapEx-related and OpEx-related emissions. In optimizing these end-to-end lifecycle emissions, and given Jevons paradox, we see that efficiency improvements alone are not enough. In fact, we find that the hardware design space becomes even more interesting when considering sustainable computing. For instance, when we consider sustainable computing, hardware design space can encompass increasing utilization with co-location and virtualization, extending the lifetime with higher reliability, and reducing wasted capacity with carbon-aware provisioning. If you're interested in learning more about this work, please feel free to reach out. Also, we will be hosting a workshop in conjunction with ISCA 2021 called CLEAR, or the Computing Landscapes for Environmental Accountability and Responsibility. I hope to see you there, and thanks for attending this talk.